Okay. Assalamualaikum and a very good morning. Salam Ramadan and welcome to our first distinguished lecture program for this year. Brought to you by IEEE Electron Device Society EDS Malaysia Chapter. I am Suhaina Muhammad Sultan from IEEE EDS and a lecturer from UTM. I'll be moderating the session today. Thank you to our distinguished speaker, Professor Dr. Nowshad Amin, for spending time to be here, and also thank you to all attendees for this session. So with citations of 7,000 plus and H-index of 40, it is an honor of me to give a brief introduction of Professor Nowshad, who is considered as the PV expert from Universiti Tenaga Nasional, UNITEN. So Dr. Nowshad Amin is currently serving as a professor at the College of Engineering of Universiti Tenaga Nasional, the National Energy University of Malaysia. He is leading the Solar Energy Research Unit under the Institute of Sustainable Energy at the same university. Prior to this, he served 11 years in the Department of Electrical, Electronic and Systems Engineering of Universiti Kebangsaan Malaysia, where he also led the Solar Photovoltaic Research Group under the Solar Energy Research Institute, SERI-UKM, until January 2018. He is appointed as an Honorary Professor to the Faculty of Engineering and Built Environment, FKAB, of Universiti Kebangsaan Malaysia. Professor Nowshad has been with IEEE EDS since 2002. With that, kindly mute your microphone and let's all welcome Prof. Nowshad Amin to deliver his talk entitled Thin Film Photovoltaic Technology from Inception to Successful Commercialization of CAD. Right? Before that, kindly be reminded there will be e-certs to all participants, so please don't forget to fill in your details in the link provided. Okay, the platform is yours, Prof. Nowshad.
Thank you, Dr. Suhana. Assalamu alaikum and very good morning. Ramadan Mubarak to all who are observing it now. Let me share my screen first. So you see the screen or?
Okay, it's nice.
Nice, okay, thank you so much. Okay. So once again, thank you EDS Malaysia for letting me share my DL talk, first time in Malaysia here, on cadmium telluride thin film photovoltaic technology from inception to successful commercialization. As graciously introduced by Dr. Suhana, I am with I'm with the Institute of Sustainable Energy of UNITEN, as well as also an honorary professor to Faculty of Engineering and Built Environment of UKM. Just taking this opportunity, I'd like to introduce IEEE EDS as a part of responsibility. That IEEE EDS is constantly promoting excellence in the field of electron devices for the benefit of humanity. And every year there are distinguished lecturer selection or approval, and I was selected last in October 2020 as one of the distinguished lecturer among 8 others. So I'd like to thank EDS Malaysia chapter for giving me the inspiration and giving me the boost for this special responsibility. And I'd like to just state the field of interest of EDS. It includes, in fact, engineering physics, theory, experiment, and simulation of electron and ionic devices involving insulators, metals, organic materials, plasma, semiconductors, etc., as well as quantum effect materials, vacuum and emerging materials. So it has a wide spectra of material science as well as device physics. So those who are interested, you can join EDS to get benefit of different kinds. Some, for example, in terms of education, in terms of publication, networking, awards, there are a lot of benefits for the members, and members can be professional member as well as student member. So you can see all the benefits from our website. And you can join the social media as well using Facebook, LinkedIn, or Twitter. So I would like to invite those who are not yet member of EDS, taking this opportunity to welcome to EDS to join for future benefits. So this is the outline of my talk today. First of all, I'd like to introduce our activities And then a little bit about the solar PV or solar photovoltaic energy technologies, because you might not be from this background. And then thin film solar PV, because they're in solar photovoltaics, there are different kinds of solar cells or solar cell materials. So I'd like to distinguish among those and taking you towards the thin film, which is today's main topic. Then taking you to the journey of cadmium telluride, which is a binary semiconductor and which has been used as solar cell material since 1970s. So I'll be giving a brief introduction about the historical advent, and then the prospects and challenges of CAD telluride from our studies as well as from other literatures. And then finally, I'll talk about the successful commercialization, because research scale is not all the one that will confine the success of this kind of activity, but commercialization is the one that took us, in fact, to the next level. And finally, I'll conclude my talk. About the introduction, as you may know about UNITEN, it's a subsidiary of Tenaga National Berhad, the sole electric utility company of East Malaysia. So we are a teaching university as well as a research university. We are taking research focus on energy related issues under 5 dedicated research institutes, like Institute of Power Engineering, Institute of Sustainable Energy, Institute of Energy Policy and Policy, then Institute of Energy Infrastructure, and then finally Institute of Informatics and Computing in Energy. I belong to the Institute of Sustainable Energy since 2018. And under Institute of Sustainable Energy, we are really committed to take lead in championing rapid decarbonization through the advancing energy harvesting technologies. And we are aligned with all those commitments like RNK12 and Sustainable Development Goals, as well as MICE-TIDE, etc. So we are quite in line with the national policy as well as international policies. Under the Institute of Sustainable Energy, we are mainly working on energy harvesting ecosystem. We are working on wind energy, solar energy, biofuel, hybrid renewable energy system, as well as sustainability, where energy sources through the harvesting technologies are there for energy applications. And I'm taking care of the solar energy research unit. We have international collaborations. This is overall ISE, Institute of Sustainable Energies in overseas collaborations, which has a number of international universities, as well as we are also having national collaborations, having a number of domestic universities, both from private and public universities. And this is about our research roadmap. I mean, next 5 years, what we are going to do in our research unit or the solar energy research unit. So in fact, our main motto is solarizing our future, as you can see on the left hand side. So we have been developing our competence in different kind of solar cells, solar cell materials, as well as devices. And then we are also taking care of PV plant monitoring, like the large scale solar farms, their failure mechanism, as well as their prediction modeling of their output. And also we are developing controllers and different kind of appliances, apart from the basic fundamental research on solar cell materials of different kinds. I'd like to acknowledge, taking this opportunity, all my collaborators, all my co-workers, starting from the Solar Photovoltaic Research Unit of ISE, UNITEN, then Faculty of Engineering and Built Environment, as well as Solar Energy Research Institute of UKM, and other collaboration partners. Ministry of Education of Malaysia, known as MOHI, as well as Ministry of Science and Technology of Malaysia, which is MOSTI, for the grants provided all these years. And also the literatures that I have referenced to make this presentation of today. And we must acknowledge that, or we must stress that we are really committed to bring this Earth as a solar green one. I mean, powered by the solar applications mostly. Here is a photo of our group taken from some weekly meetings in the near past. Currently, we are almost 35 members, including young researchers, postdoc fellows, and also PhD and master's students. And we are having almost 30 million ringgit research funding altogether. Most recent effort is about this book. We have published one book from our group members, and it is published by Academic Press, titled Comprehensive Guide on Organic and Inorganic Solar Cells. Let me share our journey, starting from my career in UKM, where I was given this small house, which was a show house that time. Then we took advantage of different funding agencies fund. I'm not sure whether you can see the, yes, it's moving. So if you enter now, it's a small lab where we try to produce solar cell materials, different kinds, as well as devices using this kind of sophisticated equipment inside a small scale clean room, class 10K. So this was our beginning, or my beginning of the journey in Malaysia. And we are enjoying international collaboration, especially from Japanese young researchers group, as we have periodical exchange programs, workshops, etc. And next is our recent fort, which is about the thin film research facility, which is located in UNITEN. If you come to PL, you can see a little bit bigger clean room is already established, and inside you can see quite a number of sophisticated equipments are there, including molecular beam epitaxy, sputtering, e-beam evaporator, thermal evaporator, and different kind of chambers to produce thin film solar cells. You can see the picture of the MBE now. And next is about the characterization lab. We have a number of characterization labs just beside this fabrication lab. I have a small video here, starting from the semiconductor defect measurement system, PL, Raman, UVVs, thickness monitor, integrated semiconductor and PV defect measurement systems, LIV, and quantum efficiency measurement systems. So there are a number of things that are already there, at least to support our thin film research in UNITEN. Is about our Greenz Park, which is an establishment for renewable energy research park, which is outside, in fact, the lab that you can see here. The BL is the one where our thin film research lab is located. And just in front of that, we have a small land, and which also include the rooftop of this cafeteria and a small land here, where the things will be like, you know, our different kind of renewable energy related installations will be there in near future. We have launched this park back in 2020, but due to the COVID situation, we could not install any of our research outcomes until now. But slowly, gradually, we are putting, for example, container lab, and also recently we got 600 kilowatt battery for virtual power plant. And things are coming one by one. So this is the picture taken almost 2 years ago. And these are the list of the lineups that we are going to set up in this small park. For example, solar energy systems for water purification, garden light and also microgrid, like some sort of microgrid here with the gazebo, etc. And also bike charging stations. So I mean, in future, I hope by the end of this year, you can see a lot of installations will be there in this park. I think UKM had the similar kind of park back in the past, but I think it is already dismantled. So I think you can enjoy our one almost in the similar pattern. And next is about the solar PV. Those who are not solar PV, solar photovoltaics, just a little bit introduction about this science or this technology. In fact, in 1839, Edmond Becquerel, a French physicist, first discovered this photovoltaic effect when he found that light-dependent voltage was detected in two electrodes, which was immersed in some electrolyte. Since then, this effort was going, and solar cells, which is attributed to this photovoltaic effect, operate converting the sunlight directly into electricity with the help of a number of materials, which are mainly semiconductors. And these solar cells can be configured into different kind of configurations like rigid, semi-transparent, transparent, flexible, etc. As you can see in this picture. A little bit inside the device physics, a solar cell is a large area diode. As you can see in the left-hand side, it's a cross-section of a solar cell. Light comes in within the thickness of nearly 200 micron. The PN junction is there, so whenever light strikes the junction region, the carriers are being energized and can be extracted out through the terminals. And we can understand the conversion efficiency by this equation, which is the power out by power in. Power in is already decided by convention, which is 1 kilowatt hour per meter square or 100 milliwatt per centimeter square as the incoming light density or concentration, and the output is the device output. Output means the voltage and the current flow from the device, which can be found from this IV curve of diode characteristics. So in fact, efficiency means that how much photon energy has intruded into the solar cell and how much electricity has been generated, that ratio, in fact. Let me show a little bit of solar cell model. Those who are from electrical background, I think you know that the diode is like this kind of equivalent circuit. We have diode equation. Then whenever a diode is under illumination, then it becomes a constant current supplier like this. So the equation becomes like this with a constant current of JL, which is light dependent current. So, and the curve shifts from first quadrant to the fourth quadrant of the Cartesian plot system. And whenever solar cell is working, it may have series resistance, it may have shunt resistance. So considering those losses into the equation, the equation becomes a little bit like complicated like this. And the curve also defects from the original structure. And just to show that that the efficiency is the comparison between the power out and power in. As I mentioned before, the power in is already from the convention 1 kilowatt per meter square as there's a concentration of the sunlight, and the output is the voltage maximum and current maximum from the diode curve of solar cell. We call it light IV curve. So from here we can also find in a different way, we call fill factor, which is the ratio of the VM-IM and VOC-JSC, which can be found from the terminal voltages of any solar panels or solar cells. Now about the solar cell development. So the first solar cell was reported in 1941 by Bell Lab, Russell Ohl, but it was only getting 4% efficiency. Then in 1956, the first reasonable efficiency, which is around 6% efficiency, was claimed by these three gentlemen on the left side, Shopping, Pearson, and Fuller from the similar Bell Lab. But that one was 6% efficient, and this cell was evaluated after almost 50 years in 2002, and which was found that 1.4% efficiency was being claimed, in fact, by the same solar cell. So it means even after 50 years, a solar cell is still working. So that was an amazing thing discovered recently, that a solar cell, how durable a solar cell might be. And solar cell technologies, I have classified into these three generations first, apart from some like application related technologies. So solar cells we can classify into first generations, which is mainly crystalline silicon based, which we also call bulk silicon or bulk solar cell. And then the second generation is mainly thin films, which requires a substrate to put the thin films of the materials of the main absorbing materials. The substrates could be glass, aluminum foil or metal foil, as well as polymer. And for the third generation solar cells, which has a wide spectra of different kinds, starting from organic inorganic combinations of dye or organic solar cell, perovskite solar cell, as well as multi-junction solar cells of the first two generations. And apart from that, too, also I have shown you that the PV application research, which is mainly on the controllers, then inverters, then solar systems, like microgrid, large-scale solar farms, etc. Our current research focuses are on the blocks here, they're shown in the red color. So we are working on monocrystalline, cadmium telluride, CIGS, as well as CZTS and perovskite, and a little bit of multi-junction, and as well as different kind of controllers. So terminologies, starting from the solar cell, it becomes modular panel. Then if we put in series, we call it a string. If we put in series and parallel combination, we call it array. So and solar systems can be individual house or even a solar car, exotic solar car, or large scale solar farm for utility power supply. So solar panels, which are commercially available right now, are shown here. Mainly first two generations like silicon based, as well as thin films, cadmium telluride and CIGS based, that you can see here, these three. In silicon also, there are different kinds of efficiency claimed by different kinds of manufacturers and different kind of materials, like in silicon, polycrystalline silicon, as well as monocrystalline silicon. So roughly in the aperture or in the panel size or panel level, the efficiency is around 20% nowadays. Although in cell level, it is over 25%. I'm just going to show you the evolution of the solar panel size in last, let me say, around 30 years of my known knowledge. So the first one on the left-hand side, you can see I purchased this calculator back in 1991 when I started my my study in Japan. So it was a amorphous silicon-based solar cell. So far I know now, it was in milliwatt peak range in one module, but now modules can be, or panels can be as large as 400 watt peak or even 600 watt peak nowadays. And 400 watt peak over is possible for thin films, even for cadmium telluride, which I'm going to discuss today. So usage wise, if I show you this one, I think it doesn't need anything to explain. So how a picture is worth 1,000 watts is again proven here. So solar panels or solar energy technologies are really taking our burden from our head, like this diesel generator by this small hat come a solar charger for the small applications like cell phones. But solar electricity is not limited to that small applications, but we can use it for residential or grid tie systems, even for the BIPV, large scale solar like solar systems can be implemented, and rural electrification, telecommunication, even satellites or space application like this, etc., are possible nowadays. So in one word, we can say it is ubiquitous. That means wherever and whatever you need, we can power it up by solar cells as long as the sunlight is there. However, I'm going to show some of our innovative PV applications that we have made in our research back in the past. For example, solar powered water purification system, solar powered gadget like cell phone or other gadget charger, even hat for the farmer, so smart home with solar car for Shell Eco Marathon, and small it's called easy bike or tuk-tuk in Thailand that is also powered by solar, as well as my small car, which is recently converted to a semi-solar, which I just take the power, some light power, to run my air condition of the car, of this Kelisa car, and it is running quite fine. And also some small chargers for laptops, etc., etc. So there could be many innovative applications. And just to show you how big the solar panel system be. So this is the biggest or largest solar farm in one single place, which is situated or located in Rajasthan, India, which claims to be 2,245 megawatt or 2.2 gigawatt range. And just to tell you that one nuclear power plant is around 1.2 gigawatts. So roughly 2 nuclear power plants can be accommodated in this space. And here we do not produce any kind of toxic toxic waste materials or any carbon dioxide, carbon monoxide gases or greenhouse gases. And in a day, roughly 10 gigawatt hour of energy of electricity is produced, and the supplier is selling at the price of 3.2 US cent per kilowatt hour to the grid. So this is the amazing figure for any electricity like producing facilities, because this is quite cost competitive among others. I'm just showing that how much PV systems or PV panels have been installed until 2020, the most recent data that we got from ARENA, it says around 709 gigawatt peak or 7,090 megawatt peak of solar have been installed. Solar systems have been installed by 2020. Just to say that in 2010, it was roughly 40 gigawatts. So you can see the tremendous growth of solar PV systems in the last 10 years. And we can also say, in other words, that we have replaced over 700 nuclear power stations, power plants, because simply we installed solar power plants instead of nuclear power plants. So this can be said in that way. And just to show here, the solar electricity price has reduced tremendously in the last 10 years. It was 0.36 US cent per kilowatt hour. Now it is around 0.1 US cent per kilowatt hour. So last 10 years, drastically the solar price has changed, and IEA, International Energy Agency, has declared that solar PV electricity is the cheapest among all other, for example, biomass, geothermal, hydro, etc., or neck and neck in other sense. It's thin films for solar cells. So let me start with this question. Okay, what is essential for an ideal solar cell? An ideal solar cell, of course, first of all, the material should be abundant, should be available at cheaper price, and we can make a solar cell device, and it will be durable, and it can harness as much as sunlight as possible, etc., etc. As well as on the other hand, it should have the manufacturability. For example, we have to make it in larger scale, larger volume, or larger throughput. So these are the requirements for an ideal solar cell materials or solar cell device. I just put in an infographic way. So in a solar cell, we need materials. We need to search for materials, either inorganic or organic, in bulk or in thin films or even in dye. And we have to look for appropriate fabrication process, different kind of fabrication process we have to try. We have to try different kind of structures. If it is semiconductor device based, like PN junction based, then we have to look after homo and heterojunction, or MIS. If it is not that kind, then we have to go for electrochemical cell. And all in all, of course, after doing all these things, we have to make sure that it is well economic. That means it is cost competitive with others. Otherwise, it will never see the commercialization aspect. So this is the thing that we must think before we proceed for any kind of new materials or new device technologies. So I'm just showing one thing here, just taking example of the materials. The materials, for example, each material has its absorption property. Okay, the sunlight is coming. This is the spectra of the sunlight. The yellow color. The sunlight is not uniform throughout the whole the wavelength region. It has a distribution. So we must make sure that the materials that we will be working or will be looking for, the solar cells, must have interoperability. That means it has overlapping with this spectra, so that absorption wise, it will be the best choice for solar cell device. So here I'm showing some of the materials like gallium arsenide, cadmium. So these are the materials that are quite good because they are quite overlapping with the broader spectrum of the sunlight. Whereas the crystalline silicon, or CIGS, has a little bit of the gap here in the long wavelength region. Now taking our attention towards the thin films, because today's talk is about the thin films. Thin films are the second generation solar cells. Usually thin films have been used for different purposes, like coating of artifacts, coating of different kind of materials, to give the durability, to give a different kind of applicability, etc. So thin film solar cells are such a kind that has been researched last almost 50 years, since 1970s. And thin film photovoltaics are just in contrast with the silicon. Silicon usually nowadays it's roughly 100 to 200 micron thick, but whereas the thin films are roughly 1 to 10 micron thick. So what is the advantage of thin film? Because it is taking less material, so material wise it is more cost competitive, and it will also solve other problems like bulk resistivity problem. And also most of the thin films materials you can see here that can absorb 90% of the incoming sunlight within the 1 micron of the thickness, whereas like for example materials like amorphous materials like crystalline silicon has it needs almost 100 times thicker layer because of their property, like we call it indirect bandgap semiconductor property. And but the key issue for the thin film photovoltaics are the long-term stability, because we are producing on top of some other foreign materials, so we have to make sure that there is high adaptability, and then the materials are not degrading due to harsh operating conditions, etc., etc. So there are still issues to be solved in thin films. I'm just showing in a infographic once again. This is the wafer thickness, almost roughly 200 micron thick. This is our here. The diameter is roughly 75 micron thick. So thin films are using roughly 1 to 2 micron in some cases, 7 microns. So roughly it is using 1 over 100th thickness of crystalline silicon. So that's why it is quite good. Now I'm going to focus on the thin film photovoltaics only, which is including cadmium telluride, amorphous silicon, and CIGS. These 3 main streams of thin film solar cells, which has seen commercializations back in the past. Let me start with our own effort, because we have started almost 10 years ago with amorphous silicon with our small facility in UKM. So we started the single junction amorphous silicon with the sputtering machine. But we designed this kind of single junction cell, and finally we have to use PECVD, which is called plasma enhanced chemical vapor deposition technique, which was not available back in the past in the UKM. So I had to use other external facility, and we produced this configuration cell, amorphous silicon cell, and finally we found 10.2% efficiency, which was the second highest during that time in 2011, I remember. So it was the second highest of that configuration single junction cell. Then thin films can be produced on glass, on polyimide foil, or even metal sheets. And this is one of the examples from our recent adventure on CZTS called copper zinc tin sulfide, which is the quaternary semiconductor. Also, we are working on CIGS, copper indium gallium selenide, which is also quaternary semiconductor, and we are trying to modify the conventional structure to this new structure in our facility in UNITEN. And the main advantage of CIS, or this kind of copper indium diselenide based solar cell, is that material usage is 1 over 100. That means we are using roughly 6.27 gram per meter square, which is, if you compare with 466 gram, you can really understand how less it is. And also for CIGS solar cells, it has an advantage of making the solar panels or solar cells in one single layout or one single lab. So in conventional silicon, somebody is making ingot, somebody is slicing it, somebody is making PN junctions, somebody is making the panels. So there are different stakeholders that takes time as well, and a lot of manufacturing processes. However, in CIS, only it takes 1/3 less, in fact, processes to make the solar cell. So of course there is a cost reduction here in this case. As I mentioned that in silicon solar cells, it takes there are different stakeholders, like someone is making ingot, someone is making wafer, someone is making cell, and someone is making modules. So altogether it takes 5 to 6 days to make a complete module, whereas in CIS or cadmium telluride, almost similar, one module can be produced in every 8 hours in the most recent technological development, as claimed by the companies. So because it is done under the same one layout, under one roof. And also in terms of energy payback, because the energy that we use to make the solar panels, so also there is a kind of idea how much time does it take to pay it back into the nature. So if you compare with the crystalline and polycrystalline, you see that CIS or thin film solar cells are the least in terms of energy payback time, less than 1 year. And if you compare with others, it is really competitive in terms of LCOE, levelized cost of electricity production. And also CIS solar cells has advantage of like the temperature degradation due to the temperature rise. It is less steep or less drastic. So it will not deteriorate even though temperature is increasing in real condition. And unlike silicon, CIS also is immune of shading effect. If silicon has some shading on partial shading on its aperture area, so the output drastically deteriorates, whereas the CIS doesn't. It has a linear degradation mode, so that eventually gives more benefit on for this kind of solar panels on crystalline silicon. Here I'm showing the efficiency improvement in cell scale, research scale solar cells of thin films only, taking 3 mainstream CIS or CIGS, and then cadmium telluride as well as amorphous silicon. So I mean, NREL or National Renewable Energy Laboratory of the US always takes this kind of effort to put the highest efficient solar cells in this chart. And it is a dream for every solar cell researchers to put their group into this chart. So since 1976, the chart has been maintained, and we can see that around 23% efficiency is claimed by the CIGS group of Solar Frontier. And amorphous silicon is roughly around 14%, and cadmium telluride around 22.1%. And I had a chance to work with Matsushita once during my master's, and as well as with the University of South Florida, who are in this chart as well. So it is quite a big deal for any researcher, in fact. Next is about CAD telluride thin film solar cells. CAD telluride thin film solar cells roughly nowadays 18 to 22% from cell to panel or module scale. And why it is a material of interest for solar cells. First of all, this cadmium telluride, it is, it's a byproduct of zinc or copper mine. So it's a byproduct. Usually people can trash it, but we can use it for a beneficial purpose like making solar cells. And because it has high absorption coefficient, it can absorb 90% of the sunlight within first 1 micron of thickness. And it has, because it's a byproduct, it doesn't cost that much. In fact, it's cheaper. And in terms of toxicity issue, sometimes people claim about the cadmium toxicity issue, but whenever it is a binary compound like cadmium telluride or cadmium sulfide, it is far less toxic than elemental cadmium. It is already proven. And if I put less amount of, because it's a thin film, so even whenever in terms of in cases of some accidents, like for example, fire or earthquakes, these panels can go into the surface water, but still the amount of cadmium which should be going into our underground, which is less than the approved level, which is around 5 ppm, even in Tokyo, which was very much, I should say, like, very much concerned about this toxicity issue because they have so many of these issues back in the past. As I mentioned, that cadmium is a heavy metal, but whenever it becomes a compound, binary compound, it is far less toxic and it is quite a stable one. It doesn't dissociate quite easily because it takes over 1000 degrees centigrade to melt, in fact. So we can use it, in fact, in a beneficial way. The first cadmium telluride solar cell, which was in single junction, was first mentioned by Vodakov in 1960, but honestly speaking, the heterojunction, which is still followed, in fact, the structure is still followed, was reported by Kusano et al. In 1963. In fact, since then, there have been so many groups trying to improve the efficiency in different kind of configurations. So there are a group from Japan, there are a group from USA, there are a group from Europe. So all together, until now, we have been able to declare 22.1% efficiency in cell level. And interestingly, last few years, since 2010, a company called Fast Solar, which is not disclosed process, in fact. So they are claiming the highest efficiency in cell and in module. As I mentioned that I have worked with 2 groups back in the past. The first one is the Matsushita, which claimed 16%, and other group is the University of South Florida, which claimed 15.8%. So More or less, I know the technology from these two groups, which we try to replicate here in Malaysia now. Now, let me tell you about the other advantages of cadmium telluride, because it can be produced as thin films by various processes. This is one of the advantages, that it can be produced by thermal vapor evaporation, and it can be produced by sparta deposition. It can be produced by spray pyrolysis, screen printing, etc., etc. So it has a wide range of deposition process, but the most, like, I should say, most the efficient one, or most output that we got, is from the closed space sublimation, is a kind of vapor deposition. So we have to produce the powder, sintered powder, and we have to produce a glass substrate here, and we have to create a temperature difference, and we have to maintain certain ambient here inside the chamber. So if we do that, then we can have a thin film of like 1 micron to up to 10 micron. If we follow some kind of temperature profile like I show here. Here I'm showing one of such CSS apparatus in our lab, and whenever we remove the glass tube, you can see the substrate holder. This is the sintered cadmium telluride powder, and this is the film that we produce in our lab. So now I'm going to show some of our experiences back from the past. This is the typical cadmium telluride solar cell. First of all, the glass through which light will penetrate through the levels, some layers of indium tin oxide, cadmium sulfide, cadmium telluride, then back contact materials. So ITO is a transparent conducting material, which is, we call it front contact. And CDS is considered as an N-type partner of P-type cadmium telluride, is a NP junction. Here is a heterojunction between cadmium sulfide and cadmium telluride. Other layers are just supporting layers as electrodes. So whenever light comes from here, we are also showing the ACM picture here, the cross section of this solar cell. And whenever light penetrates, so PN junction, the electrons will be coming through this. Holes will be coming to this to the external circuitry. So this configuration has claimed around 15.3% in our facility back in the past, and this is the QE, or quantum efficiency curve of this cadmium telluride cell, which was 7 micron thick. However, there we have to do some strategy to improve further. In fact, first thing, that cadmium telluride only needs 1 micron thickness to absorb 90%, over 90% of the sunlight. So we can reduce the thickness to the extreme limit, because if we have unnecessary thickness, it will be as a loss, as a series resistance, or sometimes it's a shunt resistance loss. So to minimize the loss, we can reduce the thickness to 1 micron. And then if we go to that extreme, then we have to do something. For example, we have to create some kind of texture TCO so that light can be absorbed well, and on the back side we have to have a kind of back surface field so that the carriers will be bounced back to the front side. So I mean, whenever we apply thickness reduction up to 1 micron, so associated things will come together. That's what the strategy were in our case. So what we did, we tried to reduce the thickness from 6 micron to 1 micron. We found that it is not that simple, because whenever we reduce the thickness, the grain size also reduces substantially, and these smaller grains are not good for solar cells because it has a lot of grain boundary defects. So larger grains are really preferential. And after certain, in that extreme limit, after certain optimization in then 1 micron thickness, we could achieve 11.2% efficiency with this nice IV curve, as you can see here. Then we implemented the texture TCO, or texture TCO, to get more light into the cattle, right? Then we found that we can absorb more, we can reduce the reflection loss, and even we reduce the thickness further near about 0.6 micron. The efficiency is roughly 11%, which doesn't reduce that much. So which was a good study from our side. And then also we try to do other things. For example, reducing the thickness of cadmium sulfide, which is an N-type partner, because mostly the carrier generation happens in the cattle, right? So if we reduce the cat sulfide thickness, we can minimize the loss, absorption loss. Like this way, we can minimize, and we can get more absorption in the short wavelength region. What we did, we found, yes, we can gain, as you can see from this spectral response, we can gain more in the short wavelength region, more current. But for 1 micron thickness, we are really suffering in the long wavelength region absorption that you can see for 5 micron is here, 1 micron is here, so we have absorption loss of this much. But it's a dilemma how you go with it. And in case of the thinner cadmium sulfide by any process, there is a chance of pinholes like this or voids in the interface region if you do not take care of the deposition process. So which will create shunt paths, and the solar cell efficiency will drastically deteriorate like this way. We also tried the grain growth for low temperature deposition process and high temperature deposition process. Low temperature usually is sputtered. Whenever sputtered grains are treated at high temperature, the grains are growing. But this grain growth is observed only for low temperature deposition process, not for high temperature deposition process. As you can see, the grains are almost similar even after the heat treatment process or cadmium chloride treatment process. I'm showing here more elaborately that whenever we produce the film, cadmium toluene film, by sputtering process, the grains are really small, even at low like power of the sputtering process. But whenever we do the heat treatment later on, after that we produce the film, we take it out, we do some cadmium chloride treatment, like putting some solutions and then heat it at high temperature, diffuse it inside, then we see that cadmium telluride film will be growing bigger. The film, that means the grains will be growing bigger, and which is quite beneficial because we can reduce the grain boundary defects by that way. And we have done it in our lab. You can see initially it was very small, but after the heat treatment at this almost 400 degrees centigrade for certain 35 minutes, the grains are growing bigger. And by that, if we make a solar cell, even making some additional layer of cadmium sulfide oxygenated, we can find 10% efficiency for 1 micron of cadmium telluride thickness. Even we measured this after 3 years, we found that this solar cell didn't deteriorate that much. So that means it is proving its so far its durability over the period of 3 years. Even we expose it outside. So this was a good finding from our research. Now about the solar cell, another issue is of this cadmium telluride. It has so many good things, but the bad thing is no good back contact is possible for this material because it has high work function, and we need some materials or metals which has also high work function. We can only find gold and platinum, which has around 5 you can see here 5.10 or 5.65, which are very expensive. Nobody is going to use gold or platinum in a solar cell. So we have to find out some alternatives. So the problem is always we can think of some pseudo-ohmic contact in between the final silver electrode as well and cad telluride here, as I mentioned here. So we are since 1998, I started working on zinc telluride, and now I see that this zinc telluride is the mainstream of commercialized product by Fast Solar. They have stabilized the efficiency of cadmium telluride by inserting a zinc telluride layer. Anyway, so I'm talking about almost 22 years ago. So I worked on zinc telluride insertion in the back contact of as the back pseudo-ohmic layer of cad telluride to have a BSF effect like this. Then if I do not dope the zinc telluride, then we got 5.7% efficiency. Whenever we dope it by nitrogen, we get around 8% efficiency. So the effect is eminent here. And also we tried to dope cad telluride. Cad telluride is a self-compensating material. That means it doesn't need any external doping. By birth, it is a slightly or lightly doped p-type semiconductors, 10 to the power 13 or 14 in the range. But externally, we try to dope it to get more like photovoltaic effect, because p-n junction, if the p side and n side it has more carrier concentration, the p-n junction effect will be more better, in fact. So we tried to dope this cadmium telluride by different process like laser annealing as well as thermal annealing. We put silver, sodium and copper in the form of solution on top of the cadmium telluride layer, and later on we try to diffuse it by using laser ray or by thermal treatment only. We found very interesting results that laser annealing didn't do that much, but thermal annealing has uniformly doped the layer. Okay, that's mostly copper, not the silver. So copper is still the best dopants for cat telluride. If you compare the silver, these are the IV curves of the silver doped cadmium telluride solar cells, and these are the copper doped. So you can see copper doped are much better than silver doped. Now let me take your attention to the prospects and challenges of cat telluride. Up until now, I told you about what we have done in the past or what we have done in the recent history. But now what should be done to take it further? Because cadmium telluride, basically 30% is the efficiency limit in a PN junction configuration. So from Shockley-Queisser limit that we usually know. So let me tell you about the historical advent by this graph. By this, it shows that back in the past, in 1970s, cadmium telluride has experienced three different kinds of development. One is the deposition process. Second is the treatment process. The third is the so-called the configuration, okay, or the material itself, improved material. Okay, so in first 10 years, deposition method was established, like CSS, closed space sublimation, or you can sometimes it is called vapor transport deposition. And then process optimization is done by cadmium chloride treatment, sometimes magnesium chloride treatment, sometimes other treatment. Now, last 10 years, what First Solar has done is mainly they improved the quality of the cat telluride, and also they concentrated on the configuration of the cell. So that's why they have claimed they have got the highest efficiency in the cell level of 22%. Now let's show what we are doing in our lab. We are now concentrating on the flexible cadmium telluride solar cells, because nowadays we see that IoT devices are flourishing. The small IoT nodes can be used as wireless sensor node for different kind of purposes. For example, agriculture, smart agriculture, horticulture, aquaculture, smart farming, etc. So we are trying to provide a small scale power supply for those nodes, and we thought that IoT nodes needs flexible solar cell than the rigid ones. So we started working on the flexible cat telluride solar cells last 2-3 years, and these are some of the results. We have started working on mainly ultra thin glass, which is roughly 100 micron thick, made by Schott, one of the German company. So here I'm showing the need for this. It's like the glass should be transparent, as well as it should withstand the different process for cat telluride, because the process will go up to 600 degrees centigrade at some point. So the glass should match those process parameters as well. So we have taken three different choices, and we found that there are two choices: ultra thin glass by Corning and ultra thin glass by Schott. So one is aluminum silicate glass, one is zinc borosilicate. We have chosen this time zinc borosilicate because it was less researched back in the past. And we have made this kind of, we have planned and we have made this kind of structure. For example, substrate. First of all, we put the TCO by DC sputtering. Then we have to make the cadmium sulfide by RF sputtering or by CVD. So like this is a sequential process for any cadmium telluride thin film solar cell. So we just follow the same way for the glass substrate of short glass. And we have followed all the process like other standard processes to grow cat sulfide as an N-type partner. And then we produced the cadmium telluride on top of that stack and checked by two different processes. One of the high temperature process, which is closed space sublimation, and the low temperature process is RF magnetron sputtering. So for the high temperature process, you can see the preferential orientation is 111 and it's a cubic phase, but for low temperature process, because there's a less energy for the coalescence or to form the grains, so it has so many different kind of grains as prominent as can be seen from it has both hexagonal and cubic mix modes in that film. And if you see under the if you see under the microscopy, you can see the grains which was grown by closed-space sublimation or high temperature growth, roughly 600 degrees centigrade, and which is by magnetron sputtering, which is room temperature growth. But grain growths are quite similar, but the quality of the closed-space sublimation is much better. Then also the electrical properties we have checked. So CSS or closed-space sublimation has better quality if you compare with the sputtered one. So here I have shown the quality of our grain of our thin films grown on the ultra thin glass with other literatures. So we found that our the CSS grown has the thickness is 2 micron and resistivity is quite okay with other baseline processes. So and other for other layers also it is also quite good. For example, telluride, CDS, TCO, and as well as I mean for the glass substrate, as you know. But main important issue here is the adhesion and resistivity, because whenever we change the substrate to a very thin glass, which is very fragile, so it lacks adhesion with the first layer. So it will be we have to be very much careful about the adhesion as well as the resistivity, because whenever there might be some contact, might be some uniformity in the joints or in the junction between these two, but resistivity may be higher. So we have to be careful about two things, adhesion and resistivity, when we are growing on top of thin glass substrates. Next, we still were working, but we just made a stack of PN junction and checked its photovoltaic property by only dark current characteristics. We found that it is a diode. That means it is a solar. It would be a solar cell as well if we really take care of the later parts. For example, the back contacts or pseudo-ohmic back contacts, then we can claim as good as other conventional cadmium telluride solar cells. Also, people are working. It is from others literature. People are working making the cadmium telluride layer in a 2 different phase. One is like, for example, band gap 1.45. One is less than 1.45 to give a little bit more absorption on the backside. So, so to do that, people are trying to put selenium. Selenium is another lighter element which can be doped inside cadmium telluride. So some people are working on cadmium selenium telluride itself, or as a combination of cad telluride and cadmium selenium telluride as a bilayer, as an absorber, because it will give the carrier more lifetime, as found by some of the research group as shown here from the PL. Okay. I'm just showing two recent papers. As I mentioned, that one of the Chinese group is working on the role of oxygen in cadmium selenium telluride thin layer in the cadmium selenium telluride cad telluride solar cell stack. So this is people are doing on that, or people are doing also on the front contact sides, where they are changing cadmium sulfide to a different buffer layer, like magnesium zinc oxide or gallium doped magnesium zinc oxide, or even zinc oxide. So these are the things that people are working now. So still it is under research from various aspects. So as a whole, what can we do? Okay, still a lot of issues are unresolved in terms of these well-researched cadmium telluride since 1970s, early 70s, I should say. So last almost 50 years we have research on it, but still there are unresolved issues. I mean, on the solar cell efficiency, because we know the efficiency can go as high as 28 to 30%. So we have to deal with the issues. For example, we have to reduce the optical loss or improve the optical absorption by the materials used in the absorber. Okay, so by these processes, and we have to use high quality material, because this cadmium telluride it is a byproduct of zinc mine. We have to purify it to the best quality, and then we have to use it in our facility, in our deposition process. We have to make the film uniform and free of any foreign particles. So this is what will lead to the lifetime optimization of the carriers and as well as the VOC optimization, or VOC increase, or the voltage increase in the solar cell. And also the carrier collection, because we have to use the good contacts. The front contact is solved, but the back contact still, zinc telluride is a pseudo-ohmic contact. Still, there are rooms to improve the back contact after zinc telluride. Usually people use silver or other mixtures. So still we can work on back contact issue, and we are working on that. Now let me take you to the successful journey of commercialization of cat telluride by some companies. Okay, first one, let me introduce you First Solar. First Solar is a company that that was established in 1999. I remember, but around 2006 or 7, it has established its biggest manufacturing power plant in Kulim. Okay, in Kulim, Kedah, Malaysia. So you can see the aerial view of the manufacturing plant. There are 6 manufacturing plants, M1 up to M6. What does it say? The scale say it has almost 4,000 skilled associates. They don't say workers. Okay, over 3 million square foot of floor space, and since 2016, every year they're producing over, I think I should say, over 4 gigawatt peak of annual production of solar panels. And this is the timeline of their development. Since 1999, it started its journey, and now it is not a simple panel manufacturer, but also it is taking care from the panel manufacturing until the solar cell recycling. As you can see that they have now installed solar large-scale solar farms, being also like that kind of entity, not just panel manufacturer, but they're also like making solar panel, solar large-scale solar farms, as well as recycling. I had a chance in 2018, I believe. Yes, in November 2018, I was invited by the Chief Technical Officer who visited from US. So he was a known person to me. So he invited me to visit their facility here, but I was not allowed to take the picture inside. Inside was as big as any football ground, in fact. So I saw how big the solar panels are being manufactured. Like some of the solar panels are taller than me, 2 meter high and 1.2 meter in width. Okay, so this quite, and all the robotic hands are making solar panels inside this facility. But I just took some photos from their display room. So these are some solar panels that are outside their facility. And here I'm going to show you one of the largest solar farm that used this cadmium telluride, okay, which in the scale of 550 megawatt peak, half of the nuclear power plant, in fact. So this is in USA, is in California. It's called Topaz Solar Farm. It started its journey in 2014, and there are so many good things about it, in fact. This company, First Solar, so far they said they have shipped almost over 20 gigawatt peak solar panels until 2019. In fact, so you can add another 4 gigawatt every year. So it will be by this year it will be 20 something. Then next is another company. This is the highest lifetime. I'm sorry, there's somebody talking. Can you? Okay, just then this First Solar, how they improved. In fact, they are now claiming 18 or 19% efficiency in large scale, in 440 to 480 watt peak range. I mean, the height is almost 2 meter, width is 1.2 meters. So how did they achieve this? In fact, they went through rigorous operational tests. Okay, they used different kind of sealing materials. The configuration is the same. Cadmium telluride, maybe they used cadmium sulfide. Sometimes they didn't use cadmium sulfide. They used zinc telluride. The configuration is same as before, but they took care of the degradation. So they used new kind of sealing, etc., etc. By that way, they improved the operational efficiency, operational output, etc. in the last 10 years. That's why they are in the scenario. Another company called Calixo, which is in Germany. They make smaller panels, not as big as 400, but they are making like less than 100 watt peak. That means relatively smaller panels, as you can see here. So they're also making, but they're claiming that their degradation in terms of temperature is not as steep as crystalline silicon. So it has definitely a good like benefit in terms of energy production in hotter climate. And per kilowatt, and per kilowatt hour of energy production, I mean, it has less carbon dioxide emission if you compare with other multicrystalline, monocrystalline, or CIS. And I'm just showing one example here that if you per kilowatt hour of energy production by cadmium telluride only produces 19 gram of CO2 equivalent, whereas other like for example coal or like oil, gas, biomass, or others, even silicon, they produce more than that. In fact, more than that, except for wind. Okay, so it is quite good news for these cadmium telluride solar cells because it is producing less CO2 emission. I think CO2 emission only due to during the fabrication of the solar cells, not during the production of the electricity. Here is as a comparison chart among the three mainstream like solar cells apart from crystalline silicon. Okay, it shows that research scale solar cells for three mainstreams like amorphous silicon, cadmium telluride, CIGS are quite okay. But what is important here to notice is the degradation. Okay, module temperature coefficient, that means degradation pattern of these four different kinds. You can see that that amorphous silicon and cadmium telluride are much less than these two, CIS and multicrystalline silicon. That means they will degrade less. They will produce more energy even in hotter climate. So this is one of the important finding for countries in desert and other hot climate conditions. As shown here, this finally impact 4% extra energy compared to silicon, crystalline silicon, and 3.9% extra energy if you compare to another kind of crystalline silicon. So this is what it says about the degradation, the degradation coefficient. Now I'm going to show you some data, practical data taken by some independent test authority called TUV Rheinland in Germany. They have put the different kinds of solar modules in three different sites: hot climate, moderate climate, as well as cold climate. Tempe, Arizona, Davis, USA in California, and Toronto in Canada. So they put different kinds of solar modules in different locations, and they ran for years, okay, a couple of years, and then they took the average. It shows that cadmium telluride has the highest performance ratio comparing to others, okay, and especially in hot climate condition. In hot climate condition, it is showing almost 0.95 performance ratio, and which is almost similar to bifacial crystalline silicon solar cell, which is quite expensive, in fact. So it is quite neck and neck in terms of performance ratio. So it tells us good thing that yeah, you can go with cadmium telluride in hotter climate, because in hotter climate it will produce more. And I'm going to show all the good thing about cadmium telluride versus crystalline silicon. First of all, it has superior temperature coefficient. Okay, 3% more energy it may produce in a year in hot climate condition. It has better spectral response. It has tracking advantage, and finally, it has an advantage because we do not use any frame. Crystalline silicon solar panels, they use frame, so there's a problem of siltation, soiling. That will introduce the shading effect, but here there is no frame, so the dust will simply fall down. So these are the advantages for advantages if you compare cadmium telluride with crystalline silicon solar panels. Now, just towards the end, I'm just going to show the thin film market share trend in the last maybe 10 years, okay, until 2019, the most recent data that we got. So in 2019, the total installation was roughly, I should say, 7 gigawatt peak, and cadmium telluride was having the biggest share of 5.7 gigawatt peak, which is nearly 2/3 of the thin film share. So that means cadmium telluride is quite a mature technology, and people have more confidence in its in its like in its energy production capacity, etc., etc. So that's why every year it has an increase in production capacity, our growth. I'm taking the comparison between all the possible solar panels or modules in the market, starting from heterojunction solar panels or IBC solar panels. These are mainly silicon based ones, they're N-type silicon based. So this shows each solar panel size, okay, for example, and the efficiency. So solar panels efficiency can go as good as 22.5% for these red ones, which is quite expensive in fact. But cadmium telluride, you can see here, which is not bad in fact, which the biggest size is around 450 watt peak, and the efficiency is around 18% in this case. So which is not bad because it is cheaper. In fact, it is cheaper than these technologies because this is quite expensive one. So it is quite neck and neck with other silicon or other thin film technologies as well, like CIGS. Now showing the overall scenario of lab scale solar cell efficiencies. So I have shown the thin films before, and now I'm showing all together just to show the place of thin films, especially cadmium telluride, among all. You can see the different kind of solar cell materials as well as configurations are shown by different colors. The highest efficiency is claimed by multi-junction 6-junction, which is based on so-called gallium arsenide based, but not for terrestrial use. It is usually for space usage, so which is 47% efficient. Okay, and we have to use 143 times of sunlight for this one. And for terrestrials, starting from here, okay, like 27.6 is solar cells. It is crystalline silicon based in cell level, but not in panel level. Okay, in cell level, 27.6% has been achieved by different entities. Then in thin film, around 23 is CIS and 22 is cat telluride. So it is quite, it is quite near to crystalline silicon, but at least cost definitely. Other emerging technologies, for example, perovskite or others, are roughly in the range of 20 to 15%. It is shown in a numerical way. So 23% for thin films, CIS, but for cadmium telluride is 22%. However, to do further, to get its latent efficiency, which we can still claim, up to 30% in terms of cat telluride, we have to give more effort on bridging between the theoretical possibilities and empirical process optimization, with a better understanding of on the limits, on the losses, on the materials, etc., which will bring ultimate success in near future. That is what we believe. Before I finish, I would like to show there was a graph. This graph was presented almost 20 years ago by some researchers that showed that prediction of each kind of solar cells by these solid lines, and the dots, different kind of dots, are for practical values of the efficiency that has been claimed by them. So by 20 something, we see that it is most of the time it is following the prediction, but still maybe we can improve thin film solar cells further to 28 or 29%, and in some of that solar cells we can go further beyond 50% in some cases. So that means we have still room to go, what to do in fact. So these are my concluding remarks. I would like to conclude by thanking you first to be with me, and then I should say that 20 years ago people were very much skeptic about solar energy, but now in 2020 we don't have to tell much to people to use solar energy. People even as well as the different government bodies are now more enthusiastic than anyone else. They are putting solar energy in their roadmap, long-term roadmap, and they want to be more carbon neutral. They have pledged to become carbon neutral by 2050, even Malaysia. So I should say paradigm has shifted to solar PV quite enthusiastically in the last few decades. Then the thin film solar PV, especially cadmium telluride, which was my talk today, has seen a lot of improvement in the last 40 years. and now it has taken some part in the production scenario. Okay, yearly production. It is also contributing some part, although it is less, like maybe 7% or less than 7% as a whole. But still, it is a promising number, because usually if we don't use the cadmium telluride, we usually wasted it. In fact, we trashed it as a byproduct from zinc or copper smelting mines. Then I should say that cadmium telluride is a solar cell. We have seen its progress by materials, by its device configuration, by different kind of structures, as well as we saw their successful commercialization story from 2 companies today. But I should say there is still more things to be done. For example, the back contacts, front contacts, even cadmium telluride itself can be deposited by other means, can be tried with different other ways. Okay, and who knows, there might be more beneficial deposition technique rather than the closed space sublimation or paper transport deposition that has been followed widely now. And finally, I should say that still there is no off-the-shelf equipment for cadmium telluride. People are making by themselves. Even in our case, our CSS is our unique CSS. We cannot find this CSS in other facilities, maybe because we designed the machine or the apparatus and we made it. And now using the machine, we are making those thin films, and we can claim up to 10% in very thin cadmium telluride layer. We have already proven record. So I should say that there are a lot of things to be done in future. And cadmium telluride is not only a solar cell materials, but also it is a X-ray detection materials. It could be used for some kind of sensors, like different kind of UV sensors. And also maybe you can, I mean, apart from it being used in nickel cadmium batteries, it can be used in other things. And also this end of life, okay, research, end of life research. That means after 20 or 25 years of lifetime of this kind of solar panels, what to do with the solar panels? We can do research on the how to efficiently collect back those cadmium telluride and recycle it, reuse it for next batch of solar panels with better configurations. So all in all, we have a lot to do, at least to reach 30% theoretical efficiency or make it more cost efficient to make cadmium telluride solar panels more popular among the people. With that, I'd like to conclude my talk showing some picture, the mosque in Cyberjaya with solar panels, and also with our motto that our mission is to re-greenify the Mother Earth with the solar applications, and which is by adopting and adapting our solar solutions for our future generation. This is my org ID. You can Google me, or even from Google search, you can find me for any kind of correspondence, and or if you want to contact me through email, here's my email address given. With that, I would like to conclude my talk. Thank you so much for your concentration. Thank you. Back to you, Dr. Sumana.
Thank you, Prof. Nowshad for thank you, Prof. Nowshad, for a very impressive lecture. I personally think that you have given a large overview of the PV technology and thin film materials, especially the cadmium telluride technology. There are so many processes and applications that I'm sure the viewers will appreciate. Okay, so let me see if there are any questions from the participants. There's one question from Dr. Nafa.
Okay.
Thank you, Prof. Nowshad. First question, with the current trend, do you think production of thin film solar cell could overpass the production of silicon-based solar cell? Okay, question number 2, how do you think China could be the world's solar panel producer in future?
How could China be solar? I couldn't hear you the second part well.
China could be the world's solar panel
producer. Okay. Okay, let me tell you, first question is about, yes, thin film has been there since 90s as small volume, okay? It will be there as a small volume again. This is my prediction. It will never surpass silicon. Silicon was there is here and will be there in future as well, because silicon has advantages from IC industry and it has already mature technology, almost 70 or 80 years of research on doping, all those things. So silicon will be there, but because as I mentioned that there are materials of cadmium, okay, which is a byproduct of some mines. If we can use as a solar panels and it, as cost competitive as silicon, so it will have its market share definitely, but the share may be like less than 10% in future as well. What we see today. The second question, as you said that yes, China, okay, the scenario changes. In fact, 20 years ago, China has nothing about solar cell research. 20 years ago, when I was doing research as a master's student, started 1996, I started my master's in Tokyo Institute of Technology, and I continued until 2001 as a PhD student. So that 5 years, I never saw any paper from China, any solar cell produced from China. But in the year 2000 onward, we found that there are Chinese production facilities, Chinese manufacturers, Chinese. Now you are getting a lot of Chinese papers. You know, mainland China is producing a lot of papers on research as well. So things are changing because China is experiencing huge research funding, and they have gained a lot of money from their manufacturing plants. So China will be manufacturing hub, but again, I said China once started cadmium telluride, but they could not continue because of the know-how. China could be the hub for silicon-based one, but the cadmium telluride has, or the thin films needs a little bit more know-how than the established silicon technology. That's why Chinese venture on cadmium telluride manufacturing started once, but closed down. And then you see in Malaysia, there is a huge, this kind of cadmium telluride. So it's because it's a knowledge intensive. So thin films and emerging technologies are knowledge intensive, which may take a little bit time for China to have well-established manufacturing facilities. That's what I can say.
Okay, thank you, Prof. Nowshad. Any other questions from the audience?
I would appreciate any kind of questions. I mean,
you can
any kind of questions. Do not hesitate for questions. I always encourage. I say no question is stupid question, because it's a question. Please ask, and let's solve it here if I can do in front of others, so that we can also gain knowledge from others.
Oh, there's another one. Dear Prof. Nowshad, thanks for your excellent thought and sharing. In view of green earth, how does cadmium telluride solar cell fit as a biodegradable device? Also, what is your opinion on the miniaturization and flexibility of cadmium telluride solar cell for IoT applications?
Okay, biodegradable. Okay, yes, thank you so much for your appreciation first of all. But about the biodegradability, we said that solar cells still now it is not. We are not using any biodegradable materials. All are recyclable. So we have to recycle it. We have to take it back. Okay, all the solar panels which are in use, which are end of life, we must take it back. The manufacturers are now ruled to take it back. Okay, and recycle it. So still, I don't see any biodegradable materials, because it in a solar cell is a stack of different kind of materials, starting from polymer maybe or glass or something. So I don't see any biodegradable material, because degradation is the one that we don't like. In fact, in solar cell, we don't want to degrade something in our solar cell stack. So we are opposite. We don't want to degrade. We want to keep it intact, even 20 years, 25 years, 30 years. So the first question is, I don't see anything about biodegradability in solar cell stack. Second issue is about, just forgot what was the second issue. The second question was what, like? Oh, okay. In a small scale
on the miniaturization.
Yeah, miniaturization. Okay, got it now.
Yeah.
So in a small scale application, yes. Because in our case, what in this one is our research we are doing on small, because we are promoting small sensor node. We already have some equipment, a small sensor node. Okay, the sensor node will be equipped. Will have to be self-sustained. We cannot give them battery or something. Okay, so sensor nodes will be deployed all over the regions, and that should be there for years. Now, only the solar cells are the solution for long term, and we do not need very large scale. Even small, you can see here one of our small, is a kind of leaf. Okay, small solar cells can work to power up one small node, which needs maybe transmission of data once in every 10 minutes or once in every half an hour. So we are working on this kind of, this is very flexible. This we used this is one is packaging, in fact, not the solar cell itself. We use very lightweight packaging, but that's why in solar cell and cadmium telluride we are also trying to make cadmium telluride because it takes different spectrum than silicon. You saw silicon spectrum and cadmium telluride spectrum is different on solar spectrum overlapping. So we want to make something where there will be multiple kind of solar cell, small solar cell device, which will be flexible. So that is our intention. That is what we are doing research on that right now.
Okay, is it okay? That was a question from Dr. Susi.
Okay.
Okay. Next question is from Professor Dr. Halina. Thank you for the excellent talk. You mentioned on the possibilities that the CAD telluride can be used as X-ray or any radiation sensors. Would you elaborate on the possibilities?
Okay. Okay, this is the knowledge that I got when I was doing my postdoc fellowship in University of South Florida. We have been also working on making some sort of film, thin film for X-ray and other, in other UV, so-called like, detection sensors. So that's what I can say. You can check some literature, but I can say that we have been making the same film for solar cell, same film for X-ray detectors or detectors, some kind of radiation detectors. So I think you can further Google or you can check the literatures, but we can make the film for you if you want. We can make the film for you. You can also check the applicability for different kind of sensors, radiation sensors. Anything else?
Okay.
Prof,
any other question?
I have a question, Hasian.
Yeah.
Yeah, nowadays we can see that a lot of application of PV to the vehicles. I mean the transportation. So from your experience, which type of PV that more suitable for the transportation mode?
Okay.
Yeah.
Let me share once again my slide towards the end, because recently I visited, in fact, 2019, towards the end of 2019, before the COVID started, I visited Japan. Toyota is going to deploy solar car, which is the car body is a solar cell. In fact, it's how can I say, integrated, or we should not say integrated. It's already ingressed, you can say. So like the car body will be solar panels. They already found that how much solar panels are needed to make, like, for example, 30 kilometer per day, roaming, for example, city use. So they already made, and they're making different materials. I can say because solar spectrum has a wide range of spectrum. We cannot depend on single kind of solar cell materials. So they are coming with multi-junction. I saw 5-junction solar cells incorporated in vertically, and it could be incorporated as a pixel. Okay, if you allow me, let me check if I can share that one. Yes. Okay. Let me share my screen once again. Why it is coming? Oh, did you see that one? Okay.
This is the last one.
Okay, this one. Okay, let me show you this one. This one is the pixel, like each dot they made on top of this is the glass. You see that each dot is one cell. So these are the pixel, you can say. So now we are making a little bit of gap, right? So whenever it will be very concentrated, okay, you will see as one color or black body on top of like solar cell or something. This is kind of solar cell that people are trying. And I should say, like, and these are the solar cells that people are trying in multi-junction. Okay, so that in terrestrial sunlight, you can absorb more sunlight vertically, so that in a small space of scar body, there will be solar cells that is enough. And I saw recently one German venture capital, they didn't do this way, they did in a different way. So their car with one charge can run for 400 kilometers. And I mean, continuously it was producing, it was getting electricity from the sunlight as well as their storage battery. So there are there are things going on, even we know or we don't know, but you may see in future that there will be car, we call it like plug-in EV, right? Plug-in EV, like so plug-ins, we could say solar EV or SPV, solar photovoltaic powered vehicle, something like that in future. But due to the COVID situation, I was supposed, and Toyota Technological University is the one. When I visited there, they said they are also working with Toyota, and maybe in future, in no time, maybe in another 1 or 2 years of time, you'll see some small cars which can run for 30 kilometers a day and completely be mitigated by solar cells. You do not have to even plug in our other power. So that you will see in no time. I believe that. Is it okay, Dr. Hazian?
Okay.
Yes, yes. Clear.
Anything else?
There is a question, Prof. Nowshad.
Yes.
Dear Prof. Nowshad, very impressive talk. For your information, we are working on indium gallium nitrides based in film solar cells. What is your comment about the indium gallium nitride based?
Okay. Indium gallium nitride. Thank you so much for your appreciation. Indium gallium nitride is the other cell, like gallium arsenide based solar cell. It's a multi-junction solar cell. One of the materials. Okay, indium gallium nitride is a band gap. Like it can absorb the high energetic photons. So you alone cannot work with the indium gallium nitride only because it's only if you see the solar spectrum, the UV is coming very less. Okay, so that's why even though you have to tandem with others. That's what we see in gallium arsenide based solar cell. They have 6 junctions: gallium arsenide, gallium indium arsenide, gallium indium phosphide, something like that. So indium gallium arsenide can be used as one of the partner of tandem structure because it only absorbs. Because you can convert the band gap and can see up to what solar spectrum it can absorb. So you can check their counterpart, like who else will do work like silicon and indium gallium nitride, for example. So it's a tandem, right? So you can work. First of all, you have to see compatibility, whether this indium gallium nitride or gallium phosphide can sit on the silicon wafer or not. This is the beginning. Then you can explore more from that. And you can make a homojunction solar, a heterojunction solar cell or multi-junction solar cell.
Okay. Okay, Prof. Nowshad, I have one question. In your research work, are there anyone working on before you actually do the process, the solar cells? So do you undertake simulation work?
Yes.
Simulation
Oh, yeah. Yes. A lot of simulation. I prepared some slides here to show that how we do the simulation. Give me a second. We do also this. If I can show, we are using a lot of simulators, markedly available simulators. I have to open some of the slide to show. I'm not sharing, right? Right now, I'm not sharing.
No.
Okay, let me share then one of the slide. Just trying to find the best slide to answer the question. Just give me another 2-3 seconds, I think. Okay, got it. Let me share once again. Okay, solar PV research. You can see, right? Can you see the slide?
Yes.
Okay, solar PV research, we can categorize. I have categorized into this like quick. Well, for example, system research you can do by using Homer software, PVSys, PVSol, PVWorks, device research. There are so many softwares. What are those many? I'll show you in the next slide. Material research you can do DFT, quantum espresso. These are the proprietary the softwares that can be used to research the material science. Okay, for the PV. These are the solar cell device simulation software that we have used from time to time. For example, something is good for silicon, something is good for cadmium telluride, something is good for CIGS, something is good for perovskite. So we have used one of those, in fact, for each purposes back in the past. What helped us, for example, we used AMS1D, and we used SCAPs for thin films. This one for AMS for cadmium telluride, SCAPs for this SCAPs is called is for CIGS. Then now what we are doing, we're trying to do DFT kind of simulation so that we can do a lot of like materials, like we can do the, for example, doping effect, for example, alloying effect from the material science perspective. Then we make it we put into the device. So this is the way of doing our new research, in fact. Are you okay?
Yeah, okay.
And these are the simulation softwares. I say there are a lot of simulation softwares you can check, and some of them are free, some of them are proprietary. You have to pay a little bit of license fee. Okay, mostly free, I think, mostly free. And you can also create your own software if you want. You can create your own software by like, there are 3 rules for solar cell. So those 3 rules, if you can maintain, you can make a solar cell software as well. Anyway, thank you. Anything else?
There is 2 more questions.
Okay.
Okay, dear Prof, as you mentioned just now, cadmium telluride is still a potentially toxic material as a composite. Could you please elaborate on the extra precaution taken by your researchers in handling this material?
Okay, a good question. I have been using cadmium telluride since 1996 when I started my master's. I have produced 750 cells by myself during my master's and PhD in 5 years. So it was used to say that if you are working with cadmium telluride, you may not have children. So luckily I have 3 kids, alhamdulillah. But again, somebody says always there are, oh, if you have, you may have children, but only girls, not boys. That is maybe true. So that is the what I can say, that cadmium telluride does not have any impact on you. In fact, someone said, one of our known researchers says, he has been working for 50 years. He's a Russian researcher from Uzbekistan. He said he's working with cadmium telluride. He's almost 70, almost 75 or something. He said, I've been using cadmium telluride since long ago, but I have no cancer. But bad luckily, his wife got cancer. I'm not sure whether these have any correlation. But joking apart, I mean, these are the jokes. Don't take it as serious. So cadmium itself, elementally, it is toxic. But whenever it is in binary form or quaternary form with other elements, it is far less toxic. The toxicity is no more issue, and the amount we are using is very less. Okay, we are not touching cadmium telluride whenever we are doing research by bare hand. We never touch with bare hand. We always put on gloves. We teach our students how to put on the gloves. Even sometimes they touch and they scratch. Even those things also we teach during the safety classes. How you put on the gloves, and whenever you are gloved, and what you should touch by a bare hand and what you should not touch by bare hand or with the gloved hand. So this kind of training we give, so that I hope that if they maintain those safety issues, they're not going to sip it, right? They're not going to touch it and then sip the cadmium telluride by their tongue or something. This kind of things will not be happening, because they are quite, I think they're adult and they know that the safety briefings are already given in the beginning. So we do not have to be worried about the toxicity issue in the solar cell labs, because we do not. There are other, like, even there are selenium, there are others. So we are using even acids. If you are using acid and you are putting your hand inside the acid, your hand will be dissolved. So we do not do anything which is not trained. So we do not we are just precaution. We are taking the precaution as same as others, as a chemistry lab, and nothing is touched by bare hand. Nothing, for sure, nothing. And always we make sure that our samples are, in the boxes, and there's no there's no way that they will evaporate, in normal temperature, because the cadmium telluride is 1000 over temperature it needs to evaporate. So I mean, overall, all in all, it is quite safe. In fact, it is in elemental, it's in binary form, it's in compound form. If it is elemental, because we never use elemental cadmium, because we buy the powder, which is cadmium telluride powder. Okay, then we sinter, then we deposit, we use the heat, all those things, and even we buy the targets, for example. So these are all quite okay in our facility, and we, of course, we're very much strict about the lab protocols. We teach them. We have yearly, this kind of workshop sessions, and those who wants to use our lab, welcome. But you have to go through this kind of training workshop to do the even characterization, all those things. So I hope my answer to this point is well enough to explain about the toxicity issue that we may face in the lab.
Okay. Thank you, Dr. Prof. Prof. Nowshad. I think we have one last question. Is it okay, Dr. Hazian? Last question.
From my side, is okay.
Before we end.
Yes.
Okay.
We can set that
So,
last.
what is the biggest in terms of capacity cadmium telluride based thin film PV already installed in Malaysia?
Oh, good question. It is the one that I don't know. In fact, the number, because I don't know whether they have there is any cadmium telluride, related, because I don't see in the website of the manufacturer. We are manufacturing. We are selling. In fact, the company is a multinational company in Kedah, Fast Solar, but I don't see any cadmium telluride solar systems in Malaysia as either experimental or in reality. So, to the best of my knowledge, I don't know the exact number. Maybe no, maybe completely zero in terms of system. Mostly, these cadmium telluride solar panels are being shipped out of Malaysia to other countries. For example, if you go to the websites of the other countries, even in India, they have a huge cadmium telluride power plant. LSS. And in USA, and if you go to the website of even Fast Solar, you can see their locations where they put, because nowadays they're taking care of the system as well. Not only they are making the panels, they don't sell the panel as a commodity product. They're selling as the system, as the end user. So to answer your question, first of all, honestly, I don't know the number, first of all, or I should say there is zero as installation capacity of cadmium telluride in Malaysia. But I think definitely we should have. We should have as a test bed. However, back in the past, almost 16 years ago, while I was in MMU, I had installed 4 different small systems. Okay, that time installed some solar panels, just one panel system to understand the operation, outdoor operation of the solar panels. Even that time also, even though I was working on cadmium telluride, I could not find any solar panels ready. I use CIGS, I use amorphous silicon, I use polycrystalline silicon, and then crystalline silicon. So 4 different kinds of solar panels I have used. Still, it is in MMU near FOE. You can go and you can check the small, rack and 1 panel system. Okay, that's it from my side.
Okay, thank you so much, Prof. Nowshad. On behalf of EDS, I would like to thank all of you for your time to join our session. Thank you to Professor Nowshad for your valuable time with us. Great honor to have you, Prof. Thank you for sharing such an impressive research works. We will email an e-certificate of appreciation to you. Thank you for everything. Before we end, can we quickly take a photo? Perhaps participants can kindly open up your camera. Dr. Hazian can help me to take photo.
Yes, I can take the photo. Okay. So I've already turned on the camera. Okay, 1, 2, 3. Okay, one more. All right. Thank you very much. Okay. Thank
Thank
you
you
for
to
joining
all
the session.
everyone
Yeah.
attending, Dr. Sabirin and also Dr. Hazian, okay, Dr.
Yes.
Suhana, Dr. Susi, I should say.
Yeah.
Thank you to you.
Thank you very much.
Thank-
All right.
Thank you, Prof. Nowshad.
Thank you. Thank you,
Thank you,
Prof.
Prof.
Go ahead.
Thank you, Prof.
Thank you. Betul. Thank you. I see
Thank you,
the
Prof. Nowshad.
faces here.
Okay,
Thank you so much.
Assalamualaikum.
Thank you. We'll meet
Have a
sometimes.
nice day.
Hopefully, we'll meet in person. It's enough
Thank you,
of this.
Doctor.
Enough of
Yes,
this
yes.
conversation. Let's meet in
Sampai Raya.
person, inshallah. Okay. Yes.
Inshallah.
EDS should have a session
Alright.
in person. Okay. Thank you so much.
Thank you very much.
Assalamualaikum.
Thank you. Assalamualaikum.
Salam.
Thank you, dear doctor.